Okay, in this video, we're going to be talking about how to evaluate limits. So, first of all, just kind of do a reminder of what a limit is. That often is written like this: a limit as x approaches something like 0 of x squared plus 2x divided by x. So the idea of this is what this means is we're wondering about what this part is doing. That's the thing I'm taking the limit of, as in this case x approaches 0. So we're not letting x equal 0, but we're letting x get closer and closer to 0, and we're wondering what's going to happen to this expression. Okay. So now notice if we were to let x equal 0, then we wouldn't have anything because we'd be dividing by 0, so the answer would be undefined. We wouldn't have anything. But that's when x equals 0. Okay. In another example, if we did limit as x approaches 0 of 3x plus 4, notice in this case, when we let x approach 0, we can actually get an idea of what it's happening here, because as x approaches 0, this thing is also approaching 0, isn't it? So as x approaches 0, we can intuitively understand that this overall expression is going to get closer and closer to 4. So this is what is called the intuitive approach to evaluating limits. Okay, because we can look at this and tell that as x gets close to 0, this will definitely also get close to 0. So the closer x gets to 0, the closer this gets to 0, which means the closer the overall thing gets to 4. Okay, but see, you can't do that over on this one, because as x gets closer and closer to 0, this thing gets closer and closer to undefined. I mean, there's no way we can do that. So what we need is some techniques for, if they're not nice and easy like this one that I just erased, if they're not straightforward like that, we need some techniques. So one of the techniques is just there's a couple of algebra moves that we know of. Like you guys have all know how to factor and cancel. So for example, in this case, notice that if I rewrite this thing a slightly different way, I can rewrite it as x times x plus 2 over x. And notice that we have these x's can cancel it with each other, because x divided by x is equal to 1. Now, of course, since x equals 0, that normally would be a problem, because we know that 0 divided by 0 is not equal to 1, but anything else divided by itself is equal to 1. So since this says x is approaching 0, that means x is not actually getting to 0, then we can go ahead and cancel these out without any problem, as long as that limit is there. So then that means we're left with the limit as x approaches 0 of just x plus 2. And that is an expression that we can intuitively figure out, because as x approaches 0, this thing here clearly approaches 2. The closer x gets to 0, the closer x plus 2 gets to 2. Okay, so that's one algebra technique, the factor and cancel. And we can use that in a lot of different situations. If we have, for example, x squared minus 4 over x plus 2, and let's say x is approaching negative 2. Once again, if we let x approach negative 2, this overall thing approaches undefined, because we'd have 0 on the bottom. So we rewrite it as a limit as x approaches negative 2, and the top I can factor that into x minus 2, x plus 2. And once again, because x plus 2 is a factor of the top, x plus 2 is a factor of the bottom, and it's not going to be equal to 0 because x is approaching negative 2, not equal to negative 2. Then I can go ahead and cancel those, and I'm left with the limit of x minus 2 as x approaches negative 2. And again, if we're asking ourselves, as x gets closer and closer to negative 2, this expression is getting closer and closer to negative 4. The closer x gets to negative 2, the closer this expression gets to negative 4. So that's the factor and cancel technique. Some other techniques we have is, for example, we have the limit as x approaches 0 of the square root of x plus 9 minus 3 all over x. So here's another situation where we want to try to evaluate this limit, and that means we're trying to figure out what is this expression doing as x gets close to 0. So again, if we try to do it intuitively, we think as x gets close to 0, this whole thing gets closer and closer to being undefined because there's no, because this I can't divide by 0. So I need to do something to change this. Now this one isn't as straightforward as the first one because you guys have been factoring and canceling since Math 140, right? This one is a little bit more unique. So what we're going to do is what is called rationalizing the numerator. Again, there's not necessarily a straightforward reason why we do this. We're just trying to make this thing look differently, so possibly you might be able to intuitively figure it out. So what rationalizing the denominator means is I'm going to multiply the top and bottom of this fraction by the conjugate pair of the top. So in other words, I'm going to write this as the square root of x plus 9 plus 3. So I'm multiplying top and bottom by the square root of x plus 9 x plus 9 plus 3. Now again, what that does is, where I came up with this is, notice that this expression here is the same as that, except for it's a plus instead of a minus. So if that would have been a plus 3 here, we would have put a minus 3 over here. Otherwise, the two terms are the same. And the reason why we do this, you'll see in a minute. So when we multiply this, notice that square root of x plus 9 times the square root of x plus 9 is x plus 9. And negative 3 times 3 is negative 9. And even cooler, this times, let's erase those so you don't get mixed up. Negative 3 times that plus 3 times that is equal to 0. And that's why we multiply by the conjugate pair, because it basically eliminates the radical. So we're left with just that on top, and on the bottom we have x times the square root of x plus 9 plus 3. And now, of course, 9 minus 9 is 0, so we're left with just an x on top. Oh, I've got to write my limit there. Limit as x approaches 0 of x over x times the square root of x plus 9 plus 3. Okay, and once again, we have x is a factor of the top, x is a factor of the bottom, so I can cancel those out, and I'm left with the limit as x approaches 0 of 1 over the square root of x plus 9 plus 3. And now we're going to go ahead and try to use the intuitive approach and say, okay, if x is approaching 0, that means this expression right here is going to get closer and closer to the square root of 9. And the square root of 9, of course, is 3. So this whole thing is approaching 1 over 6. Because we'd have 3 plus 3. So the limit of this expression, the limit of this right here, is equal to, as x approaches 0, is 1/6. Isn't that interesting? So this method is called rationalizing the numerator. In your past mathematical lives, you probably rationalized the denominator a few times because you were told you couldn't have a radical in the bottom of the fraction, so we use the same idea to rationalize the denominator, but in this case we're rationalizing the numerator. to make the fraction look a little bit different and hopefully cancel some things out like we did here, and then be able to evaluate this limit using the intuitive approach where we just let x approach whatever it's approaching and we can kind of see what happens to the numbers. Okay, I'm going to show you one more algebraic technique, and that's simplifying complex fractions. So that would be where if I have a limit limit as as x approaches 0 of 1 over x plus, 1 over 3 plus x minus 1 over x all over x. So there's an interesting problem. Once again, if I let x approach 0, the bottom gets closer and closer to 0, and I don't really have a good way to handle that. So because it's just going to be undefined, I can't think about what it would be. So I'm going to, again, try to change the way this expression looks so that I could possibly try to handle it again using the intuitive approach. So whenever we have complex fractions, a smooth move to simplify them is just to multiply top and bottom by the common denominator of all the fractions. So in this case, we have two denominators. So the common denominator would be x times 3 plus x. So that's what I'm going to multiply top and bottom of this fraction by. So when I do that, I get the limit as x approaches 0. And notice when I multiply, so I multiply both terms by that. So when I multiply by this, the 3 plus x cancels out, and I'm left with just x. And I have a minus, so I'm going to put a parenthesis there so I know the minus applies to everything. When I multiply this by that, the x's cancel out, I'm left with the 3 plus x. Of course, in the bottom, I have x squared times 3 plus x. I want to put each there. Okay, so then I notice that x minus x is just 0. So as x approaches 0, I get negative 3 on top, and I get x squared times 3 plus x on the bottom. And notice when I did this, nothing happened. I mean, nothing good happened, actually, I guess I should say. That notice when x approaches 0, the bottom still gets closer to 0, and there's nothing I can do about that. I mean, I can't think about what that would mean intuitively. Well, actually, let me think about this for a second. Could I? Because if x is getting closer and closer to 0, and the top is, or if x is getting close to 0, that means the bottom is also approaching 0. So we have something that's set on top, negative 3, and the bottom is getting smaller and smaller and smaller. What happens to the overall fraction as the top is set and the bottom is getting smaller and smaller and smaller? So think of like negative 3 over 1, and then negative 3 over 0.1, and then negative 3 over 0.01. Of course, this is just negative 3. That is going to be negative 30, right? That is going to be negative 300. So you can see since the top is set and the bottom is getting smaller and smaller and smaller, that means the overall fraction is actually getting bigger and bigger and bigger. In fact, it's going to get big without bound. The smaller the bottom gets, the bigger the fraction gets. So this is going to head towards infinity, and since the top is always negative 3, that means it's going to head towards negative infinity. So there's 3 different algebra techniques. We did the just factor and cancel. Then we did the rationalize the numerator. And that's a very useful technique when we have a square root in the top of the fraction. And then here we multiply top and bottom by a common denominator to simplify a complex fraction. And again, in all cases, we got it down to where something we can intuitively work out what the limit would be. Okay, so that's a short video on algebra techniques for evaluating the limit.